we start with the lecture proper. And we have seen the last time how we would model Bernoulli distribution with a neural network and a multi-Bernoulli distribution. And today we want to look at how can we learn a Gaussian mixture model using neural networks. And Gaussian mixture models are a very popular way of modeling distributions. They often come from a combination of several underlying distributions. For example, let's assume we have objects that we want to describe or recognize, and an object like we have this example with the dogs, and we may have different types of dogs. Yeah, we might have very small Chihuahuas. We may have very large Bernardine dogs, and if you describe them by something like weight or height, they're very different. And well, we can have more shepherd's dogs, etc. You know, you can think of very different types of dogs with different characteristics, but they're all dogs. So if we want to describe the whole class of dogs, it's not good to just say dogs are in a certain range of weights and heights. It is often, not always, better to describe such a class by a multimodal Gaussian. So let's say that here we have a height, and let's assume the Bernardine dog, the very large dog, takes a height which is, for the adult dog, on the higher end. And let's assume the Chihuahua takes a height which is at the lower end. And you see here for a Bernardine dog what is the probability density for being in a certain range of heights, and correspondingly here for the Chihuahua to be in a certain range of heights. And maybe the shepherd's dog would be somewhere in between. Now, what is the overall probability for dogs in general taking together these different kinds of dog? It is basically the overlay of these three different kinds of dogs, if it would be exactly three kinds. And with this overlay, what we get is a probability density that is shaped like 2 or 3 or 4 or 5 combined Gaussian distributions. And this is exactly what is a Gaussian mixture. It is a mixture of several Gaussian distributions, and of course one has to normalize how many exemplars are in this area of Chihuahuas, how many Bernardines, and so on. So you have to normalize with which relative frequency they occur. But what you then get is, for these different heights, a different kind of density, how often a certain height shows up. And this is very nice then to describe such a kind of animal in this case, and you can compare it to some cats, and the cats would have a different Gaussian mixture model distribution. This can of course not only be done in one dimension, this can also be done in 2 dimensions. So you may have, for a particular class of dogs, 4 different distributions that are characterized by heights and weight, for example. And of course you could have rather tall dogs which are rather slim and therefore don't weigh that much, and the other way around. But of course typically you would not just have an equal distribution in both of these 2 directions, but you can have a relatively complex shaped landscape which you approximate well by such a Gaussian mixture distribution. Now, how can we learn this? And what you can do, basically, when you build a neural network, you can think about what do I want to learn? How do I put these things together such that I adapt my weights to achieve a certain target distribution for the objects I want to describe. So the objects you want to describe all come with an input layer of a certain size, whatever this is. In the simplest case, this could be the height and the weight of such dogs. It can be something very complex. Then you have a linear layer, so this would be a hidden layer as we have used, and potentially a default representation is that all of the inputs from the input layer are connected with all of the hidden neurons from this linear layer. And then you may repeat that. And now we want to go beyond this simple feed-forward network where we have the linear and then the activation function, and we do this several times, in that we model something which has certain properties. And what do we model here? We model here that given certain input, what if the input takes a certain shape? What is that? Whether the class belongs to a certain number. Let's assume we have 3 different variations for dogs and 3 different for cats. Yeah, we might want to model how probable it is that a certain input falls into one of these 6 different Gaussian original distributions. And then here you only model what is the underlying Gaussian. But then you also have to model for the d many dimensions, the d many classes that you have, the corresponding mean, the mean value of these different Gaussians. And well, the mean, of course, is to be modeled in many dimensions. For example, here you would have d equals 2. You have a mean where you have an x1 component and an x2 component. Well, and so for the first Gaussian, you have the x1 component and the x2 component, and the second, and in general you have n many times. For as many classes as you have here, you have to model the corresponding mean. Now the question is, what do you do for each Gaussian about the covariance matrix? There are different choices. One choice, which is often done, is to simply say, I assume all these covariance matrices are identity matrices, that they have unit shape, they all have the same width, for example. That's of course a very coarse way to model this. The advantage of modeling it this way is that you don't have to learn the parameters for the covariance matrix. The other extreme is that you try to learn all the parameters for all the covariance matrices. So again, for this picture here, your covariance matrix would be 2 by 2 because you have to model how the x1 dimension and the x2 dimension are correlated with each other for each of the 4 different Gaussians. So this would be 4 times a 2 by 2 matrix. And the diagonals, the strength of the diagonals basically describe how much variance do you have in the x1 or x2 direction. And the off-diagonal entries describe how much they are correlated with each other. So now if these covariance matrices can become quite large, especially if you have many dimensions. If you have 100 dimensions, you have a 100 by 100 covariance matrix, giving you the need to learn 10,000 parameters. That's typically too much. You don't, first it's very compute intensive, and second, you may not have that many objects to actually even learn them appropriately. So quite often what one does is not the unit, the identity matrix, but that you use a diagonal matrix where you just describe how much variance you have individually in each dimension without considering the covariance between the correlation between the different dimensions. Yeah, and when you look at the covariance, right? So, for example, if you say you have this covariance matrix, you basically describe that around a certain value. If this is x1 and this is x2, the lines of equal probability density would be something like this, because in the x2 direction you have more variance than you have in the x1 dimension. And of course, correspondingly, well, this is of course happening. So these would be the kind of lines of equal density, with the highest density being at the origin, if the origin is your mean value. And so the diagonal matrix, of course, has only as many entries as you have dimensions. So in this case, d equals 2. So you just have to learn 2 parameters other than the parameters for the mean value. So this is actually something which is done quite frequently, that you have this diagonal matrix that you learn, but you don't learn that x1 and x2 would be correlated. Okay, now these are all, I mean, what you do is you allow for learning by introducing parameters here, like a hidden layer here, the probability that a particular x belongs to one of these classes, the means for these different classes, and the covariance matrix. And now in the output layer, you put all this together where you describe what is the probability that a certain input belongs, or what is the probability that you produce a certain value. And the probability of producing a certain value for a certain input is basically given as the probability described by the normal distribution for this y, given that the object is described, and here we have descriptions for the different the different Gaussian distributions. So we would have in these 2-dimensional pictures 4 of them, and each of them has a mean, and each of them has a covariance matrix, and there is a probability that this object belongs to the class 1. Then you take this Gaussian distribution, the class 2, you take again the corresponding second Gaussian distribution, and you multiply every time the probability from the specific Gaussian distribution for this particular input value y, given that you are in that you would belong to this particular region. And so this gives you the overall formula. And so the probability then for a specific object to have a certain value is then simply the integral over the value times their probability, the conditional probability. And of course we cannot work in continuous space, but our computations are always discrete. So we turn this continuous representation into the corresponding discrete approximation for these n different classes. We just look at how probable each class is, and what kind of probability do we derive from that. Yeah. That's what we want to do. Now the loss function influences the means. Well, we need to formulate the loss function such that we correct the means until we best represent all the objects that we see. It influences the choice of the categories. When I'm in a certain place, I want to do a maximum likelihood choice. And a mean should be only corrected if its category was influential. I mean, if I have one Gaussian here and one Gaussian there, and I see another object here, it makes sense to adapt this mean value, but not this one. And I mentioned already these different strategies for the covariance matrix. The simplest one would be constant, that you just use the identity matrix. The second one that you learn the diagonals, like these ones here, but the full is rarely used. So this is just one glimpse into the fact that you can model such kind of complicated decisions. How probable is it now that I observe a dog of a certain height and weight? By adopting all my different parameters. And of course, in the end, I do a kind of maximum likelihood estimate where I optimize my cross entropy with gradient descent. So what you now need to understand at this point is that we have to build these different building blocks. Like, what is a loss function? Cross entropy, or if you want to do regression, squared error. You have your gradient descent that you use to change the parameters in order to minimize this loss. And now we have an architecture that can become very, very complex, but you don't care about it as long as it's all nicely differentiable, or at least differentiable in almost all points. Then you just throw this gradient descent at your modeling problem and let the parameters be adjusted. Now, practically speaking, you will still have the challenge that for a specific model, your model may be benign in the sense that it could be in the best case convex, where we have determined that if you have a convex problem, your local optimum that gradient descent will run into will also be a global optimum. You potentially, depending on your model, you could also have a model that runs into many small local optima, and you don't get an overall very good model, where you would then need other strategies for regularization to not overfit to the particular observation of data that you have in your data set. Okay, so now the question, how do we do this gradient descent? How do we, in such a complex model, adjust our parameters? And the key vehicle for neural networks is backpropagation. First, what we do is, in order to do a prediction, is we do forward propagation. Forward propagation means we have here some input layer, some x1 and x2 for a particular object. Then we forward the value. Here we have the connection to the next hidden layer, and on all these edges there are weights. We have here a function that sums up the linear contributions from the input, and likewise here. We have an activation function like ReLU or 10H or something like that operates on this linear aggregation. And then we have a particular model to determine the output layer. We have seen, for example, softmax when we want to classify, or we do again for regression just another combination of linear plus activation function. So the forward propagation is nothing else than just computing with the parameters that we have along these different edges. That's it. And then we end up with a result at this y. What this result means depends on your architecture, depends on your choices. I mean, here on this previous slide, there's one meaning. What we define here is a conditional probability given the x, what is the density of the distribution in this particular place. So how probable is it that we see such a kind of x? But in another place, you model something differently. Now, when you have computed a particular y, you consider you compute your loss. There is one y which is in your data, and there is now this y hat that you computed, where you predicted a value. And by comparing the label y versus your prediction y hat, you compute the loss, depending on the loss function, of course. And now the idea of backpropagation is that there is a mistake that you do here, well, the loss, and you backpropagate this loss along this chain of computations. And what you do, I mean, what we have seen so far is that, for example, with the perceptron learning, we basically had parameters that produced some mistake, and we computed the loss and switched them in slightly direction in order to reduce the loss. We do the same here, but we don't stop at this layer, H1 and H2, but here we also determine that the value of H1 and H2 has some loss, and we further propagate to the previous layers and the previous parameters. So we determine the gradient for all our parameters such that the loss here in the output layer becomes smaller. Let us look at very tiny examples, toy examples, just to make it easier to understand. We can do all kinds of things. Let's say here we have a computation graph where we do multiplication. We have input x, input y, we multiply these two values, and the result is z. By the way, what we do this not only to be small, but what we do here is we symbolically describe the process of doing the forwarding. I mean, this is the computation graph, and the computation graph describes what value is combined with which other value before the next operation happens. And when I describe logistic regression, I can describe this with such a computation graph. Namely, logistic regression is nothing else. I take an input and compute the dot product with some weights. This gives me U1. By the way, these are all vectors in the general case. Then I have some offset, some bias that I add together with this product to get the U2. And then I apply the activation function sigma to get my prediction of my logistic regression, which says, okay, probability for the one class versus probability for the other class. So the syntax elements of my computation graphs are nodes represent variables. Some of these variables I have invented in order to represent my intermediate results. Like in the logistic regression, we put all this into one term. But if I put all this into one term, I don't have these intermediate values that I compute. Obviously, for logistic regression, I do compute this product. But it's not explicit. But here I make it explicit. And then I have edges with labels, and they represent the operations. Always when two edges converge in a node, I just take the input from these edges and I use the corresponding label, here the plus, in order to compute the next intermediate or the next final result. Here is the whole thing for a ReLU layer. Now, of course, this can become quite complex. I could even describe this for a matrix X, where each vector in this matrix stands for an object, and the different columns stand for different objects. So I can even consider all of the objects at the same time. I have here my capital W, which is not a weight vector, but a weight matrix. And I can compute with matrix multiplication the next matrix here. I take the bias that I add to all the different results. And by the way, this weight matrix, of course, would use the same weights for all the different inputs. Maybe we can also just formulate this as a vector. And then I add my bias vector, and then I apply element-wise ReLU to get here this output, which will be the next hidden layer. So, in order to understand the algorithm that comes next, what I have already used here is some notational convention. We sort our nodes topologically. That means if some computation happens before some other computation, then the intermediate node is before the other intermediate node. Right? I have, of course, when I consider such an input layer and some hidden layer and then some next layer, and if I have here a fully connected layer, which means that all this layer feeds into all elements of the next layer, and this is true for all of them, so this would be fully connected, right? And likewise here. It doesn't really matter whether I compute this first or that first, but it matters that before I compute something here, I compute something here. And so I have a topological sorting that must consider that this result is computed before some result is computed here. This topological sorting, of course, there is some freedom. Yeah, again, it doesn't matter whether this is computed before that or this before that. Okay, so what is now the convention? I start with the input layer. This is the X. This is my U1. This weight vector down there. This is my U2. And the offset here, this is my U3 for the offset. The next layer then is U4. I index as being this node, and U subscript 5 is this node. So you see basically this sorting U1, U2, U3, U4, U5. You have this layer, and then you have the next layer. So these computations always built on computations that have happened before. This has a larger index than this, namely U5 versus U4. I have, for a particular node like U4, defined the ancestors. A stands for the ancestors. The ancestors of 4 are U1 and U2. This is U4, this is U1, and this is U2. So I have an ancestor relationship. And U5, this is this one here, has the ancestors U3, this is this one here, and U4, this is this one here. The ancestors of 6, this is this node here, is just U5. And then I have operators at the nodes that have ancestors. So F4, this one here has as an operator the dot, described here. And F5 has as an operator the plus, described here. And F6, this is the node 6, has this operator sigma, described here. And then U6 is our output, which is what we predict. So this is the convention, as also described here. And, well, in general, of course, the output layer may have more than one node, but that's what happens. So how do we do the forward propagation? We don't operate on the input. So for the nodes starting with k plus 1, where k is the length of the input, so here that would be 3. So starting with the node 4, we go according to the topological sorting through all the different nodes. And at each of these nodes at which we have to compute something, we look at the ancestors or the parents, I should maybe say, and we compute the value by taking the corresponding operator and apply it on the set of all ancestors. So take this operator dot and apply it to the ancestors, the immediate parents. So this is the forward propagation. Now, why do we do this kind of symbolic structure? What we later on want to do is we want to backpropagate. So here we have done forward propagation. Now we have a loss here, and now we want to distribute the loss, to change the parameter to make the loss smaller. So what do we want to do? We want to change the value of z in the direction of w, for example. So w is the weight vector that we use for some example input. Now what you see is that this prediction and this w, could for example be this w here, that they are very far away from each other. But what happens is that in order to compute the direction of z in the direction of w, which is the gradient in the direction of w, well, how can we do this? We can do it by taking z in the partial derivation of z in the direction of y. So y, the change of y influences the change of z. Then the change of y in the direction of x, so this is the partial derivation of the value of y in the direction of x. This is how does a change of x influence y. And then how is x influenced by w? This is the partial derivative of x in the direction of w. And what you see here is we have a chain. In this simple example, it's a direct chain. In general, it could also be split in different directions. And what you also see here is that this term is the same as this term, because this derivation of w and this cancel each other out. And these cancel each other out. So the core idea is to say that when we are interested in the change of a parameter, we can construct such a value by looking at all of the individual intermediate steps. And we have the same arithmetic term. It is maybe a little bit unusual for you, not for a mathematician, that, well, we just work with these infinitesimal small values in the same way in which we work with numbers, where this would be quite normal. Yeah? But this is actually fully workable, that we expand this term to turn it into individual computations or derivations that we can master directly. Now, when we look at these three terms, these partial derivatives, this is nothing, and here this is a simplified example from the neural network book. Here we assume that we always have the same operator f. Could be different operators also, of course, then we would have different f's. Here we use the same f here and here and here. And then this, of course, is f prime of y. And f prime of x and f prime of w. Yeah, the partial derivative of, for example, here, this is nothing else than f prime of w. Now, what is f prime of x? F prime of x is f prime of f of w. I compute I take this value w, I apply f, this gives me the value x. So when I'm interested in a partial derivative here, I have f prime of f of w. Down here I have f prime of w, and up here this is nothing else than f prime of f of w. So this is the forward part, and this is the backward part. Now, what you see here is we do back propagation by looking at how should I change this parameter w in order to change the value of z. And this w in this case is down here, but it could also be here or someplace else. We compute this intermediate structure. And now this intermediate structure may use the same kind of operators on same input. For example, here we have f of w and here we have f of w. And now what we want to do with backpropagation, we don't want to compute f of w multiple times, because every computation where we have to do something, well, incurs some overhead. This is a tiny network and just chosen to illustrate the principle. In a large network where you compute the same values again and again and again, this repeatedly computing such a value like f of w would not be very efficient. So what you do is you look at what is in my backpropagation the common structure that I need, and then you share such kind of values in order to avoid redundant computation. Okay, again, now let's do backpropagation truly in such a tiny example computation graph. Here, this is just one part of the of logistic regression, but it doesn't change when it gets larger. It's the same thing. So let's assume we have input x equals 1, y equals 2, and the target is we really want that the prediction up there would be 3. But right now it's not 3, because if we multiply 1 and 2, it's of course 2. So the prediction for our current set is not 3, but it's 2. And when we increase our prediction, then we reduce the error. given that currently we have this label of 3. Now when we have the mean squared error, because we do regression, then the loss function, so the loss value is taking the loss function between the predicted and the true value. Well, that of course is 1/2 the prediction minus the true value squared. Well, the difference here is 1, so this is just 1/2 is the loss value. Now, on this loss value, we want to produce the gradient. We want to change, for example, these parameters here. I mean, if this is the input, this may be the weight, for example. So we may be interested in how can we change the loss. So how should we change the prediction in order to change the loss? This is nothing else than the gradient on this loss function. And well, this is the loss function, of course. And when we compute this, then this is nothing else than we take this exponent to the front, 2 times 1/2, and then the inner function is z hat minus z. So this is nothing else than z hat minus z. Z hat minus 3 equals minus 1. Now, let's assume we want to change both of these parameters. I mean, it's really, you have to look at what parameter you want to change, but let's say these were both parameters. Then you would compute the gradient in this direction. If only y is the parameter and x is the input, then of course you would only take the gradient in the direction of y. So, and the gradient of that in direction of xy, well, this of course requires the partial derivatives, and the partial derivative first in the direction of z hat, and then in the partial derivation of z hat in x, and then you compute this, and then of course in the direction of x, that means y is a constant, and therefore it's minus y, and y had a certain value, namely 2, so it would be minus 2. And likewise, in the other direction, then x is the constant, therefore this is minus x, and this has a value, and that's up here, therefore it's minus 1. And so you increase these parameters, and with increasing these because you subtract these negative numbers, and with subtracting this direction, you get closer to the set. And you do this with some learning step. You do only go a small step in the direction of changing the parameters. So if, well, y was a weight, it should be increased. The y new is the old y minus this gradient. Eta is a learning step, some small number. Maybe here it would be 0.1, and minus 1 was the gradient that you computed here, this one here, minus 1. So you would increase y to be 1 larger, and then actually when you do, well, not 1, because it would be like 2.1, for example, and then you would have reduced the loss. What I described to you here, sort of like backpropagating this loss, this is what you also do in a very large network. And here is, for this larger example, first the forward. So you have your input layer, then you have the next layer, the hidden layer 1 is nothing else than taking the operator on the vector of values, and this f is typically some activation function, or is activation function based on this linear combination where h0 is the input layer, this is the weight matrix, and this is the different biases for the different hidden layer here. So you initialize H0 to be the input layer, and in a layer-wise step, layer by layer, you compute the next linear component by taking the corresponding bias vector plus the weight matrix times the previous layer. Why is this a weight matrix? Why is this not a weight vector, but why is this a weight matrix? Because? Yeah, it's a bit too generic answer. Exactly. This is the correct answer. So I just repeat. Between every node in the preceding layer and every node in the next layer, we have in this fully connected network a connection. And for each connection, we need a weight. I mean, the weight could in general even be the same in all the different places, but we really need for every connection here, for every edge here, we need a corresponding entry. And so if we have here n many nodes, and here we have n many nodes in the hidden layer, we have n a matrix of n times n. Of course, if we have like here on n and here we have m, then of course we have n times m many entries. Yeah? Every pairing requires a corresponding weight. And that's what is described in this weight matrix. That's why the input layer here, we have one value for every node here. Multiplied with a matrix, it means that for this node, all the inputs here are summed up according to the corresponding entry, the corresponding vector in the weight matrix that describes exactly the weight aggregation for this node. And likewise, another weight vector for this node, and so on and so forth. And then you do this element-wise application of the activation function, this f. So that's what you do stepwise. And the last layer is then your prediction, and your loss value, your j, is applying the loss function between the prediction and what you know as the true value. And then typically we also do regularization, just as with linear regression. Now, how do we do backward, this whole thing backward? So after the forward computation, now we compute the gradient on the output layer. So that's what I showed you with the tiny network. So we compute this y hat is the output. How does should the output be changed to change the loss value? What is the gradient of changing the output of applying this loss function between the prediction and the true value? This becomes our gradient g. And now with this gradient g that follows after this prediction, so to say, we go into our backpropagation. And backpropagation works backwards from the top layers to the lower layers. That's why we count from layer L to layer 1. This is layer L, and this is layer 1. So we convert the gradient on the layer's output. The layer's output for this one here is just this g. But for this layer, this is the gradient that was computed here. But every layer between layer L and layer 1 has such a previous gradient. And so the layer's output, so this one here, this was above. And now we have this nonlinear activation. And the nonlinear activation, you remember, was some f of a, f of ak. That was nothing else than the f of the corresponding, if I do it pointwise, it would be a weight vector times the previous layer plus some offset. Now, if I compute the derivative for that, the derivative is just this f prime, and I multiply this pointwise, element-wise, with the gradient that I get from above. And this gives me the gradient in the direction of ak. And this is my next gradient for my previous layer. So I took the gradient I had here and turn it into a gradient here. And so I go from this hidden layer to this hidden layer to this hidden layer. And what I always compute here is basically how do I have to change this, this output. But what I'm really interested in at this point is not changing this output, because that's something which is computed. What I'm really interested in is changing my weights, the weight matrices and the bias vectors. The weight matrices at the kth layer, the bias vectors at the kth layer. And this always is, what I want always here is the gradient of the bias or the gradient of the weight matrix at this layer as it influences the loss value j. This is the loss value j. And as I move myself back here, this is nothing else, this bias, once I have overcome this f of fa of k and I have updated my gradient, then the bias linearly influences here. Well, this is this linear influence on the current gradient that I have. This is why this update is nothing else than the gradient. And here I have some regularization. About the regularization we will talk later. And for the update of the weight matrix, this of course is influenced by the values on the previous layer times the gradient, and again plus some regularization. The bias node is not influenced by any previous layer, but the weight matrix is influenced by the previous layer. And then one has to propagate the gradient one layer down. If we now have updated these weight connections, we now have to move the gradient that we have about the values here to the gradient about the values here. And that's what we do in this step. The next gradient is the gradient of the hidden layer before of my loss value, which is nothing else than the weight matrix transposed of the gradient. So, and here I've just, this is the same slide here. I've used this to explain this, but when you want to read it up from the book, this explains this also in text. So this, I've just included this for convenience, so you can more easily look at the explanations. So this is a kind of vanilla approach to doing backpropagation. And this vanilla approach does not reduce the computation. What I said here is that we want to save computation efforts because some of the elements are needed several times. And this is not considered in this vanilla implementation. Now, when we do backpropagation, and here is a simple example again, because for a large example it gets quite complicated. We can look at what are these computations that we have to do in each different step. So what we need at this point is we need to compute how does the value Z change with regard to Y. And at this point, we want to compute how does Z change with X, and for this we need how does Y change for X. And this depends on the value of X. And here we want to compute how Z changes with W, and for this we need how does W change with X, but we also need how does Z change with X. Yeah, we need this and this in order to compute this. So you see, whereas the forward structure moves from the bottom to the top, the backward propagation moves in the other direction. And what you also see is that we now can basically push these values through this backpropagation graph, where some of these values might also be used several times in general. So, by the way, when we compute this thing, we also need it here. In the naive implementation, we might, well, I think in the other one it's okay, but in the most general case, we might not recognize that we compute this just once. And with such a computation graph, we identify it and compute it really just once. How do we ensure that we compute these values just once? And this is then done by dynamic programming. Do you know what dynamic programming is? Yeah, so some people not, others don't. So the brief rehash would be, in dynamic programming, you break down your problem into subproblems, and for every subproblem, you store your result. So here we have subproblems, and you compute values for these subproblems, and you store the values for these subproblems. And when you encounter the same subproblem again, you don't have to compute it again. You just use a hash function, a hash array, for example, to retrieve it. And that is done in this algorithm that generalizes and therefore avoids double computation. So here you have now additional data structures. So like this V, the variable whose gradient should be added to T, and the grad table. So you here have this table in order to store intermediate results. Here, this is the graph to modify. G prime is the restriction of G to nodes that participate in the gradient. And you have this data structure that maps nodes to their gradients. And if now a particular node is already in this table, then you just return the entry. So that means if available, you just look it up, else you have to compute it. And then if you have to compute it, well, you go here. And therefore, you also just look along this computation graph, this one here, and compute the next values. So we will not ask for details of this slide. So this is why I don't go into details of this, but hopefully you get the general idea of this dynamic programming approach. Okay, so much about backpropagation. Questions about this here? Okay, if not, then yeah, sure. Okay. Do you take a note of that? And then you can bring this to the into the discussion group for the exercises. Of course, in general, when we require such an exercise, you can choose the simplest solution. Yeah, you don't have to do the most elaborate construction. So then it would make sense for you to look at the vanilla algorithm, for example. Okay, so now you know how you can optimize the parameters of your neural network. There are some inherent problems in that. So to optimize the parameters is a rather ill-posed problem. Do you know what an ill-posed problem is in general? It is one where you don't have the one unique solution. Yeah. And indeed, we don't even know whether, when we define such a neural network, whether there exists one global optimum. And with a kind of strategy, I mean, what we do is a hill climbing strategy. Well, for those who have been to Introduction to AI, several search strategies are described, and we have a complex landscape for our parameters, and in general, we don't end up with the globally best parameter setting. So ill-posed because there may be many solutions. It's even unclear whether there is one best solution. Actually, there is even the idea that we could have different models and they could be better or worse in different circumstances. So people also do ensembles of neural networks. I mean, you know ensembles already. When we looked at bagging and boosting, and you can even do this with neural networks. And again, that's one method of countering overfitting. We have very many degrees of freedom compared to linear models. I mean, when you look at ChatGPT or the likes, we talk about hundreds of billions of parameters. This is really extreme. Even if you don't go that far, I mean, you may easily have millions of parameters. The counterpart to that is that a deep neural network is especially useful if you don't have previous knowledge. If you have like a feed-forward network, you don't have much of a bias towards the one or the other model, which is problematic if you want to learn with few examples, but which is good if you have a lot of data and you want to learn with a lot of data a very precise representation. And you don't need background about that you have a Gaussian or power law or whatever. And especially people have struggled to model images, audio, and text. And these are the areas where neural networks are by far most successful. When you think of typical database entries, I mean, people also apply neural networks there, but one can say that with typical database entries, the tree-like methods tend to be at least as good, if not better, than neural networks, and they are much faster and require less training data. The problem with images, audio, and text is that it is unclear which features to use. When you have a database entry, you have something like weight, it is rather clear what this stands for. When you have a pixel value of an image, what does a pixel stand for? Nothing really, right? You cannot say that the pixel in this corner of an image represents a dog. Really, you first need to discover features like particular texture that suggests there is some fur or a tail or something like that. You need to first discover this from the pixel representation. And the same, of course, is true for audio and even for text. I mean, people for a long time have struggled to build feature methods for images, for example, came up with descriptors like SIFT or SURF, they call. These were like the best descriptors people had in the 2000s, in the zeros, and they were not very good. They were not very good to describe actual objects. And now, I mean, what we will also look at briefly is CNNs, convolutional neural networks, is one method, for example, that do not take pre-formulated feature methods like SIFT or SURF, which look at where are certain kind of edges in the picture, but they learn which features are good to distinguish a cat and a dog. They are far from perfect. They work very differently than what we as humans understand then as cat and dogs, but at least they are as good such that one can do object recognition with superhuman performance. Let's look at neural networks. Example first for a challenging example, which is handwritten character classification. And handwritten character classification, in the meanwhile, performs better than human handwritten classification. So I have to say I'm not aware of a freely, openly available tool. Some of the current language models support handwriting recognition themselves. Still, I mean, one has to add that the neural networks do a bit better than the humans, but not much. And for humans, it's actually sort of simple. Well, depends, is it simple or not? I'm not sure, because clearly kids spend quite a lot of time to learn writing text and reading text. So I'm not even sure that it's so simple. But for us, as we have learned how to decipher text, I mean, it's very easy to read this different piece of text. From a conventional machine learning perspective, what makes it difficult to read such a sentence like the quick brown fox jumps over the lazy dog? It's that we have a very large intra-class variance. So here, these are all examples of A's. And some of these A's, I mean, this could almost be a Q. So the intra-class variance is high. The A's look very different. And the inter-class similarity is also high. This A might even be a Q in a different context. And this is also typical for an area where you want to apply neural network to discover features based on the features that you can then apply classification or other kind of predictions. Here another example for the G. Yeah, some G's might look almost like a gamma or a Y, and again, the intra-class variance uh, is very high, and inter-class similarity is also high. Here again, O and A sometimes hard to distinguish. What is actually also quite funny, you see here when you just take this sign, it's a bit unclear what it even is, but when we read this, it's clear for us it's dog and not dag. In this context, DAG is even meaningful, directed acyclic graph, yeah, but not in the context of this sentence. And what is quite funny is when my partner, she is an English teacher. She uses also some of the language models to scan students' essays, and the one problem, and using that as an entry for the grading and the corrections. The problem is that the language models sometimes correct the mistakes. So if, like, the student would mistakenly write an A here instead of an O, the language model would tend to correct this already. And so she wouldn't recognize then, if she only relies on the transcribed text, that there was a mistake here in the first place. So this is a bit like a human capability then. Okay, so how would we feed such a neural network? For handwriting recognition, we typically would have different pixels, and every pixel would have a corresponding gray value. Of course, such a cell might have an intermediate gray value. And so you have an input layer which has as many values as it is wide times high. So L times W many entries. So Xn is, the N here is L times W. And so this is your input layer. Then you have hidden layers, and at some point an output layer where with softmax you could distinguish A, B, C, Z, etc. Now the question, of course, is which architecture do you want to use? Do you want to use such an architecture? We know from the universal approximation theorem, if you have enough neurons here, it will work. It will work if we can train the weights well enough, which is a challenge. We assume always that we have a certain number of training samples. And yeah, these are the weights that we want to learn. And then, of course, we just provide this as input and predict values and then derive label, because this, for example, is the highest prediction value from the softmax. And then, of course, what we have to do is we need to define a loss function and apply our gradient descent. Now, here is an overview over the loss functions that, well, the models and the loss functions that we may want to use. So what if we want to have a binary output type, so class 1 or class 2? Well, then we would have a Bernoulli output distribution, and we talked about modeling Bernoullis last time. The output layer would just be a simple sigmoid based on one neuron, and the cost function would be binary cross entropy. We have a label which is either 0 or 1, and we would look at how far are we away from this binary cross entropy. We could have a discrete categorization that would correspond to a multi-Nulli distribution. We also looked at last time. And we would have as an output layer a softmax, which would work like this here. And then we would use, again, not a binary, but a discrete cross entropy with a higher number of classes. If we have a continuous output type, there may be different models that we could use. We could use a Gaussian, or a mixture of Gaussians, or some other stuff. We will not look at these, but at other ones. An output layer would maybe just be linear from the preceding layer, and we would use a mean squared error, for example. When we look into modeling of probabilities of belonging to one or other class, then we would maybe look at cross entropy. And well, then here this becomes specific, so I don't go into this here. Okay, so now we do this gradient descent with our model as described here in this matrix. But there are a range of problems. First, it matters how we initialize our weights. So where is our starting point for the weight matrices? It is typically not a good idea to start with weights of 0. I mean, when you look at the algorithm, you would multiply many parameters with 0. And it may work, but a typically better way is to initialize your weight vectors in your different weight matrices around a value of 0, but with a standard deviation of 1. And a standard deviation of 1 would mean every entry would then have this kind of standard deviation. And HL is the width of layer L. You could also, instead of random weights, choose each weight vector to point in a uniform random direction. So you would have a length 1, but a random direction. And you choose the biases randomly such that the ReLU hinges cover the input. So you don't want that they all put your predictions in a certain direction, because if they are all in the same direction, you may not have any or not much information. For small data sizes, we just compute the loss and then the gradient. Typical methods as I showed you. And now for the gradients, I showed you the default method to be used in backpropagation, but there are more sophisticated ones. There are basically the gradient method. All have the Newton's method as their ancestor. And you remember Newton's method is basically used to find the intersection with the x-axis. You have here some function. You have here your x-axis. You are at a certain point, and you want to discover where this point is the one that you want to discover. You use the gradient at this point, and you end up here. And so you are here closer to this intersection of the function with the x-axis than you were here. And then you iterate this method, and by iterating, if the function has a nice shape, you come closer and closer and closer to this point. There are some problems you may encounter. For example, if your step size is too large, then you may go off in the wrong direction. If your function has a very funny shape, you may go off in the wrong direction. And there is a very large literature about how to make Newton's method faster. And LBFGS is an old one that works well in many circumstances. Now, when we want to minimize the loss, we can relate this minimization as finding the minimization of a function. This would be here. Minimization of a function is the place where f prime is 0. And that's why Newton's method, which determines the intersection with 0, can be reduced to the question of where does f prime of x has a 0 value. And so how do we approximate this? We think, that's the idea of Newton's method, of the Taylor expansion. We are at a point, and when we go slightly off that point, we can describe the value at this off point as the value we have at the point xt plus, and here comes the Taylor expansion. And the Taylor expansion looks at this polynomial of epsilon, epsilon square, epsilon cube, epsilon to the power 4, and so on. And we have this Taylor series, which for f prime, x of t times epsilon is one part of the approximation. And then you have 1/2 of f double prime of xt times epsilon square. And then this Taylor series continues with the third and the fourth, and so derivative and a polynomial epsilon cube and to the power 4 and so on, with decreasingly factors here. And if we look at this, we can do what I just said, namely derive and set the value of x to 0, of f prime to 0. So 0 is the derivation of all that, where this, of course, is just an approximation because the series here is cut. And if we do this, then this becomes simply f prime. This is a constant. So this is dropped. This is simply f prime of xt because this is a constant, and the derivation of epsilon in the direction of epsilon is then 1. So this part. This part is where this is a constant, and you take 2 times epsilon, and 2 times 1/2 is 1. So that's f double prime of xt times epsilon. And if we have this equation, 0 is this, then we can compute epsilon as epsilon is, simply by reformulating this equation, is f prime of xt divided by f double prime of xt minus. And therefore, when we want now to approximate the place where this holds, that the derivation of 0 is 0, then we define the next x where we approach the minimum more closely as the previous x plus some epsilon, and this epsilon is defined by this value that we have computed here. Okay, so what do we do here? We use the gradient to go down the hill, but if we know the second derivation, we can jump more closely to the place where we intersect with the x-axis, or where then the minimum is achieved. For this, however, we need to know this second derivation. The second derivation is, of course, easy when we have just a one-dimensional function, but of course, in general, we don't have a one-dimensional function because we have these vectors that we deal with. So when we do this in several dimensions, we have this gradient of f of x, which is defined by the partial derivations according in all the different xi directions. I mean, for an image, this may be 10,000 pixels, so 10,000 directions. And this is the first derivation. When we do the second derivation, what we get is the Hessian, the Hesse matrix, and that takes the gradient and computes the second partial derivatives in all possible directions. So the Hessian matrix is defined by having in each entry two partial derivatives, and well, these are indexed just by the column and by the row in the different x directions. Oops. If we now compute the next x, we take the old x plus some learning rate, the inverse of the Hessian times the gradient. There are several problems with that. One problem is that computing this Hessian is quite compute intensive. Already computing the gradient is an effort. The direction, let's say here we have 10,000 x's, 10,000 pixels, that's 10,000 entries. The Hessian would be 10,000 times 10,000. So we would have 100 million entries for the Hessian. So for such a kind of an example, you probably don't want to use the Hessian. If you have a smaller dimensionality, you may want to do this. And then the thing that you want to avoid is to compute the inverse, because computing the inverse of a large matrix is very compute intensive. But of course, you can reformulate this as a linear system, and then you solve a linear system of equations. And when we express this in a graphics, then the gradient descent is like this green line. If these are equal values of f, the green line goes down the steepest way. But the steepest way does not necessarily lead on the shortest way to the minimum. And when we know about the Hessian, we can take a shorter way to the minimum of this function. And so the shortest way might be here, this way along the red line, which is not necessarily the steepest descent. The Hessian, by the way, is symmetric, obviously, because it doesn't really matter whether you first compute the partial derivative of j and then of I. Turning this around doesn't change the entry, so it's symmetric. And then the Hessian may be convex or concave, or neither of the two. So when you have some nice quadratic forms, then this can give you very nice computational solutions where you have some guarantee how you solve your problem. But in this situation, there's a whole optimization theory behind that. And if there's a lecture on optimizations, not a single, a whole lecture series on optimizations, you might want to consider looking in there. So, and of course, as I said, don't compute this term, but rather solve this linear equation like this. So you have a linear equation solver that finds these values. At this point, I stop because I'm already over time. And next week, we still have a few slides on stuff like convergence. Let's stop here. Have a nice week.